If I asked you to tell me where a point is in two-dimensional space, Cartesian, you would tell me like that, right? So I could tell you a point has coordinates 3, 4. I could tell you another point has coordinates 1, 0. And I could tell you a third point has coordinates -2, -5. And that is basically how you tell, oh, we should focus here, how you tell if some, it's distracting, how you tell if someone is, let's try it again, where a point is in 2D space. It's unique. I mean, I don't know how long ago you learnt coordinates, but probably quite a while back. Is this my eyesight? Is this thing focusing in and out all the time?
It is focusing in and out.
That is very annoying. Okay, well, I'm easily distracted person, but I'm going to try and see if it won't distract me. So let's look at how you tell someone where an object is in 2D space. And we use a thing called polar coordinates. So imagine I'm trying to tell someone where that point there is. Then I tell them two things. I tell them an angle called theta, and the angle is the angle starting at the x-axis and moving anti-clockwise. And then I tell you a thing called the distance, which we typically use r, and that would be that guy. So I could tell you a point A, and I would do it something like this: 5, 30 degrees, 4, pi upon 2, 1, negative pi upon 4. Now these are examples of polar coordinates. Now they still use two numbers. The first number is the distance from the origin, and the second number is the angle that you make with the x-axis. Seem reasonable? So, I'm not doing this accurately, but at least it's a guesstimate. If I wanted to do 5, 30 degrees, can you imagine that you make a line that has a 30-degree angle with the x-axis, and then you go along this line 1, 2, 3, 4, and you get to guy number 5, and that's where A would be. So can you see in this way that you can tell any object in 2D space using this new coordinate system called polar? If I wanted to do 4, pi upon 2, isn't pi upon 2 actually 90 degrees, so it goes straight up the way, and it would be roughly, it would be about there, right? Now, 1, negative pi upon 4, let's look at that last one. The angle's a little bit unusual because you are allowed to put any angle you like there, including negative angles. Wouldn't negative pi upon 4 be going clockwise pi upon 4? And then 1 would be just go 1 unit, so there is C. So our first question, I guess, is, are we all comfortable with this new fella, this new coordinate system called polar, and that it allows you to give any point in 2D space? So let me add a little sting in the tail here. When you do these guys up here, they're called Cartesian. They have an obvious property. It's unique. See if I tell you the point 3, 4, and that guy there is 3, 4. Isn't that the only way you can tell me in Cartesian that point? There isn't another pair of numbers that will get you to the same location, right? 3, 4 is 3, 4. That's it. It's not true, however, that when you use polar coordinates, that the answer is unique. In other words, a point in space can have more than one polar coordinate. Right? It's the same point in space, but you can describe it in more than one way. I'll give you an example of that. Suppose I had a point who was 5, 30 degrees, right? In fact, it'd be that guy there, right? 5, 30 degrees. Five, 390 degrees. Do you know that's the same place? Because you just go round the circle once and then you do 30. And couldn't I keep on adding 360s to that forever? And it would still be the same point in 2D space with lots of different angles. Not a very natural way of doing it, but technically isn't 5, negative 330 degrees also that point? If you go clockwise, 330 degrees, it's the same as going 30 degrees anti-clockwise. It's the same point in space, which means that when we are talking about polar coordinates, there is a theoretical infinite number of different ways of telling me where a point in 2D space is. So you can imagine that there's going to be a rule to stop everybody picking their own favorite version, so that we all kind of end up writing the same version. That makes sense? And the rule is quite simple. Make that positive. And make theta between 0 and 360 or 0 and 2 pi. Now, does that seem like a reasonable rule so that we all end up getting the same answer? Right. And so we would talk about the standard polar coordinate. Right. The standard polar coordinate is the polar coordinates at that particular point using this restriction. Now, there's one version of that restriction I haven't used yet, and that is a negative R value. And you might think, how do you get a negative R value? Well, let's see if I can show you how you would get one. Suppose I had a point that was negative 3, 80 degrees. Right? So this, as we know, is the R value, and this angle is the theta value, right? Now you do an angle of 80 degrees. Now if R was 3, if this was 3, wouldn't you just go 1, 2, 3 and you'd finish there? But it's negative 3. So instead of going in the direction of 80 degrees, negative 3 says, go 3 units, but not along the 80 degree one, kind of walk backwards 3. 1, 2, 3. So it is possible to have a negative R value. Do you see how it's going to work? Make the angle first, but instead of going in the direction of the angle, go the exact opposite direction, whatever the units are, right? Negative 3, go backwards 3, negative 1, go backwards 1. And going backwards, I mean, go that way, right? And the last little thing, zero comma 0 degrees. In polar coordinates, where is that point?
Isn't it just the dead center?
Yeah, it's the origin. Does that make sense? You don't move any angle, and I guess that's the x-axis, right? You know, if you don't move, 0 degrees is the x-axis. And then how far away from the origin do you go, the r value? Well, the r value is 0, and theta is that. Now let's look at these two guys. Zeros can cause people problems because sometimes it's hard to get your head around it. 5,0 degrees is not the origin. If you sketched 5,0 degrees, wouldn't 0 degrees be the x-axis? And then can you imagine going 1, 2, 3, 4, 5? Do you see it's basically on the x-axis 5 away? What's 0, 20 degrees? Where is it?
The angle's at 20, so we're not too far above the 0, really.
Not too far?
Only 20 degrees above it, but I don't know. It's not.
How far away from the origin do you go? You're right about the 20 degree part, right? So you turn 20 degrees and off you go. Try and visualize that. There's 20 degrees, allegedly, right? So how far do you go along that 20 degree ray?
Just hang out at 0.
So where are you?
At the origin.
You're at the origin. In fact, isn't 0, any angle you like at the origin? 0, 10 degrees is the origin. 0, 50 degrees is the origin. 0, negative pi upon 2 is the origin. So if the r value is 0, you will always end up at the origin. It doesn't really matter which angle you use to project. Whatever that angle is, you don't leave the origin, right? You go 0 distance. Which means that 0 is probably the weirdest polar coordinate in the world. The origin is the weirdest polar coordinate world because technically, just like all the others, aren't they an infinite number of them? As long as they all have a 0, something. So that's the beginning part. Let's move on to conversions. How to convert polar to Cartesian. How do you convert an r, theta to what we're more used to, an x, y? Let me show you where the formula comes from, because I could just tell you the formula, but I want to add a little bit more detail than that. Imagine we have a point P whose coordinates are x, y. And it's called r, theta, right? So it's got both ways of describing the point, right? R theta or xy. Now, if I take this guy and I draw a little dotted line, I make a little right angle triangle, agreed? And what's the distance from here to here? That's the x coordinate. And the distance from here to here is the y coordinate. Are we getting a little deja vu here with this triangle? Now, this angle in here is theta, and this distance is r. Right? So I've got my picture with both coordinate systems kind of interlocking with each other, right? And we're going to use that to try and find formula that allow us to get the x coordinate in terms of r and theta, and the y coordinate in terms of r and theta. So let's go for it. If this is the angle theta, won't we call this the opposite, this the adjacent, and this is the hypotenuse, agreed? And won't the sine of theta be the opposite over the hypotenuse, right, from SOHCAHTOA? And so the sine of theta will be y over r. Great. Now, if I do a little cross multiply there, do you see that we can get the y coordinate by going r times whatever the cosine of theta is? That seems sensible. Without me going through the entire process again, how will I get the x coordinate?
Cosine instead of sine.
Can you remember doing some questions a few weeks back? Remember that the x coordinate on the unit circle, right? On the unit circle, isn't the x coordinate cosine and the y coordinate is the sine? Now, if the unit circle, that's r equals 1, is expanded to a circle of radius r, do you see that's the adaptation to the formula? The x coordinate will be r times the cosine, and the y coordinate will be r times the sine. Now, as long as you give me angle theta that exists in the unit circle, then I can find the exact values for these. If you just give me some random angle like 22 degrees or 1.7 radians, I can still get the answer, but can you imagine in those cases, I won't get an exact answer. You know, x will be 1.77 and y will be minus 2.2. Right, so there are two distinct types of questions here. Exact value questions and decimal answer questions. Exact value questions will happen when theta is in the unit circle, right? So when I tell you theta is 30 degrees or pi upon 4, you can get exact values. Decimal versions of these questions will be, I tell you that it's 5,22 degrees or 3,1711 pi, right? Things that are not in the unit circle. And in those cases, it's really just do it in your calculator and you get the decimals that you'd expect. Any questions about what we've done so far? Does it feel a little bit more deja vu-like in the sense it doesn't feel like we've done too much new stuff? We're just regurgitating things and concepts we've used in other places. Well, so let's do some practice at just that. So I'm going to pick a couple of polar coordinates and then turn them into what they would be in Cartesian. Right? So let's suppose, for my first example, I gave you 5, 30 degrees. So this is r, this is theta, obviously. Then its x coordinate is r cosine of theta, and its y coordinate would be r sine of theta. So far, so good. Now in this case, r is 5, and the angle is 30 degrees. Okay, you need to have your unit circle handy, as probably you should have for every section we ever do. What is the x coordinate of 30 degrees?
Three over two.
Say again?
You said the x for 30 degrees?
Yes.
Or 3 over 2?
Well, you're breaking up, but I think you said root 3 over 2. You did, okay. Which is basically the answer, and the other one's a half, so I guess you should call it 5 halves and 5 root 3 over 2. Would you agree that that was pretty painless? So we've done our first conversion, right? How about this one? We have our polar, and we're going to turn it into essentially Cartesian. So our x coordinate is this fella. And our y coordinate is this fella. Now, do you see this formula that we have here doesn't care if r is positive or negative, and it doesn't care if theta is radians or degrees. Just make sure you use the right answer when you do it. And it actually doesn't care if theta is 22.1 pi or negative 45 degrees, right? The formula is pretty resilient. You don't need to accommodate for anything. And you got a formula, you plug in your chug, right? Now, cosine of pi upon 4 is root 2 over 2. So this is negative 2 root 2 over 2, but in this case, you see it simplifies. And this fella here ends up being the same guy. So it looks like negative root 2 comma negative root 2. Are you comfortable with that particular guy, right? I think I was talking, it was Skylar I was talking to, but in general, everybody. Chapter 8, the 3 sections that we do in Chapter 8, a lot of people find this section much easier than, you know, the last few weeks, because you've been fighting your way through some really complicated stuff, right? But this stuff, I don't think, unless you try and read too much into it, right? Unless you try and make it hard for yourself, it's pretty obvious what you should do, right? There's not a lot of places to go weird routes. Go. Let's check this one. What do I mean by checking it? Right. If I plotted the point negative root 2 comma negative root 2, it would be about here, right? Roughly. Now, negative 2 comma pi upon 4, right? Would you agree that pi upon 4 is this guy, right? Now, if you were going 2 comma, you'd be up here, right? But the r value is negative, so don't you go down here? Do you see it matches where it should be? Right? It's in the third quadrant, 2 units in the opposite direction from what pi upon 4 is pointing. So, I mean, if you have a weird one, you could check that. I think for completeness sake, all I'm going to do now is a kind of decimal version, right? We've shown you how you deal with converting from polar to Cartesian that have exact values because the angles are in the unit circle, right? And let's put one which hasn't a chance in heck of doing it. So suppose I had the point 3.1, 17.1 degrees. Would you agree you're not going to get an exact value from this question, right? That's not the way this is going to work. But in a lot of ways, it doesn't really matter. The x coordinate is going to be r times cosine theta. That's going to be 3.1 times the cosine of 17.1 degrees. And the y is r sine theta. And that's going to be 3.1 times the sine of 17.1 degree. Just for speed, I'm just going to do it on my calculator here. There's only one way that I can screw this up. Anybody want to tell me what I might be doing wrong in my calculator that would screw this up?
It's in radians.
Yeah. Have any of you done it yet, that you're in radians when you should have been degrees? Because I do it a lot. Yeah. So you know yourself. Just have a quick look. And I just had a quick look, and I got lucky. It was in degrees, right? So I'm happy with that. But I should always look. So here we go. I'm doing a 3.1. I'm multiplying it by the sine of 17.1. And to 3 decimal places, it's 0.912. And the second guy is a 3.1 again. Oops, I put that in the wrong place. I guess there's 2 ways to screw up. Putting the answer in the wrong place was the other one. And if I go 3.1 times the cosine of 17.1, I'm looking at 2.963. Well, do you feel comfortable about a question that would be something like, convert the following polar coordinates to Cartesian coordinates?
Kind of. I had one that had 103 pi over 4. That was kind of weird. It's a big number.
103 is just big. Oh, okay. 103 pi over 4, that one? Okay. This doesn't matter, but do you have that number and I'll use it?
Yeah, it's 4.
4, okay. This angle is in the unit circle. That way I'm going to get an exact value. You might think, what angle is he? Can I tell you he's 25 3/4 pi? A 100 gets you 25 and 3 left over, right? If you keep taking away various versions of 2 pi, will you agree that you eventually get to 1 3/4 pi? Take away 2, 4, 6, 8, 10, 24. And isn't that 7/4 pi? So what I'm really going to do is I'm going to make this question 4 comma there. Now that guy you can use because he's in the unit circle, isn't he? He's in the 4th quadrant. So if the angle they give you is, I'm trying to think when that works here, if they give you an angle of 750 degrees and you want to do a conversion on it, shouldn't you probably take 750 degrees and get it back to the 0-360 range, right? So we've done that way back in week 1. Don't you take away 360 and then take away another 360 and you do it until you get the number you want? Or you take away 2 pi and keep taking away 2 pi until you get the number you want. So yeah, thanks for bringing that up. I never covered that, but that's essentially how you do it, right? If the angle's negative something, don't you just add 2 pi or add 360 until it gets to a place that is in your unit circle? Right, so if it's a negative 425, you just keep on adding 360 until you get where you want. We good now? Thanks, Skylar. I forgot that choice. So let's do the reverse. How do you take Cartesian and convert to polar? Okay, let's get this. That is weird. Right. My internet connection is unstable. Are you getting stuff for me right now?
Yeah, just blurry.
Right. I have no idea what the heck's going on here. I'm trying to think, how are we going to get around this problem? I'm going to see if I've got anything else that is using up bandwidth apart from my wife. And I'm certainly not going to tell her to go off the internet. That would be a bad move. Well, she's actually working from home, so she needs it as well. So, where are we going here? I'm trying to just switch off anything that might be overtaxing my machine. Okay. I just have to go. I'm going to try my best to draw it, but you're probably going to get most benefit just hearing me because you won't be able to see it well. If you want to convert Cartesian, right, to polar, we already know that x is r cos theta, and we know that y is r sin theta. And if I built my little triangle with the y going here and the x going here and the r, right, like I did last time. We're good? So what I'm going to look at this is there a way that I can find a formula for getting r and for getting theta? And there is. According to Pythagoras, won't r squared be x squared plus y squared? That makes sense? Pythagoras? X squared plus y squared gives you r squared. So if I rearrange that just a little bit, can r just be the square root of the x coordinate squared plus the y coordinate squared? Okay. So that blob that you can't read because it's very blurry is r equals the square root of x squared plus y squared. Will you trust me? That's what it says, even if you can't read it. Now, this picture up here. What is the tangent of theta equal to? Well, according to SOHCAHTOA, it's opposite over adjacent. Agreed? Opposite over adjacent. Well, in this case, opposite over adjacent is that. So the tangent of theta is y over x. Seem reasonable? Now it's went to small screen. Great. So won't theta be the inverse tan of y over x? And there is our second guy. So how do I apply these two formulas to a conversion question? Suppose I wanted to plot or convert the point 5, 5. Then won't r be the square root of x squared plus y squared, which is the square root of 25 plus 25, which is the square root of 50, which we all know can simplify eventually down to 5 root 2. Are we good? Now, the tangent of theta is y over y, which is 1. I tend to use this way around. Rather than call it the inverse tan, I just say to myself, okay, tangent of theta is 1. What angle has a tangent of 1? That's in your unit circle. If you go hunting for it, you'll find it. Does anyone know what that angle would be?
It's pi over 4.
Correct.
Right?
Or, you're right, it is pi over 0.4, or, because remember there's always two answers, right? So here's a little thing that you have to do with this type of conversion that you didn't worry about in the earlier conversions, right? Only one of these two answers, that bloody pi upon 4 or that bloody 5 pi upon 4. So how do you decide which? You do figure it out by the quadrant the original point is in. If I plotted the point 5, 5, wouldn't it be in the first quadrant? And so the angle I want is the pi upon 4 one, because it is in the first quadrant. You know what makes sense? 5, 5 is in the first quadrant, so the angle I want should be the first quadrant. Suppose this question,
yeah.
right? Suppose this question was -5, -5, right? Now, do you know that this would end up being the same number? And wouldn't this end up being 5 quarters? Because where is the point -5, -5? It is in the third quadrant. So when you're looking for what angle has a tangent of 1, there will always be two choices. One of them will be the correct one, the one that's got your point in the same quadrant as it. So if your original point is in the first quadrant, you want pi upon 4. If your original point was, say, in the third quadrant, then you need to find the third quadrant angle for theta, right? In that case, it would be the 5 quarters. That makes sense?
Yeah.
Right. So when you're finding the angle, say again?
No, I'm just trying to adapt because I came in so late and I'm so mad about it.
Well, I'm having mad thoughts about why this bandwidth is low since I pay a bloody fortune to allegedly have very good bandwidth. Evidently somebody's downloading 14 Amazon movies and they're using my Wi-Fi to do it. Actually, I should think about that. I should check my Wi-Fi and make sure it's got a password on it.
No.
That's an interesting thought. I wonder if that's exactly what's happening. Some bloody bugger is stealing my Wi-Fi bandwidth. Right. Okay, focus. Right. So let's do another. Oh. They heard me. They stopped doing it.
No, it's still bandwidth is low. At least from my perspective, it is.
Yeah, but I can't help your bandwidth. This is my bandwidth. This is good.
Okay.
I got my guy back. Not only is somebody stealing my bandwidth, which is scary, they can even hear me talk, and then they are, oops, I better not steal it right now.
It's the NSA just checking in.
Well, I have nothing but lovely things to say about the American political system, and the fact that I'm not an American citizen shouldn't distract them from letting me stay here. So I got my bit in there.
Can
Okay.
you put these notes on Canvas after?
You mean these scribbles I've got? Yeah. I'll try and put them in order. I think I should be able to do that. I'll use the cam scanner thing, right? And I'll just put it as a PDF. So those blurry ones won't be blurry. I guess that's a good idea. Okay, let's do another one then. Darn it, it's hard to actually do these guys with exact values. So I'm trying to think of one that would work with an exact value.
Hey, Donald.
Yes.
Are you going to be doing some of the weirder questions? Like, I think late into this section, there's like one equation that's like 6x equals 6y.
Yeah.
Okay.
I'm going to try I'll do two more of these guys, and then we're on to the last part, which is how do you convert formulas into polar, which is what that x equals 6y thing, I believe is about.
All right, thank you.
Okay, I need to find one. Okay, I'm just biting the bullet. I've got root 3. Darn it. I 1 over root 3. Well, you're getting what you're getting. If, whoops, let me start again. One half comma root 3 upon 2. That might work. I'll make that guy negative. Okay, so there's my x coordinate, there's my y coordinate. For reference, because we'll need to know this later, what quadrant is that guy in?
Third one? No,
Okay,
no,
so-
fourth one.
Right, so if you did a little sketch of it, it would be down here, so it's in the 4th quadrant. Why is that going to be important? Remember, when we get theta, I'll have 2 choices. One of those choices is guaranteed to be in the 4th quadrant, and that's the guy I'm going to use for my theta, right? So that's why that's there. So if you want to get r, it's the square root of this guy squared plus this guy squared, which gets me 1/4 plus 3/4. Am I good or am I good? It's 1. Now, the tangent of theta is the y over the x, so it's this fella over this fella, which ends up being that fella. Right, there is an angle in the unit circle, right? There's an angle in the unit circle whose tangent is negative root 3.
It's at 5 pi 3.
And where's the other one?
Is that 2 pi 3?
Oh,
What's it? Yeah.
yes, well done. Which one of those 2 is the guy that we're going to use?
The 4th one? No, the one in the 4th quadrant.
Right, so this one here. So our answer is going to be 1 comma 5/3 pi. So far, so good. Right, I'm going to actually skip the next one because we only have about 10 or so minutes left, and I want to go into that last part. When you're doing the one I'm missing would be something like 7.1, 6.2, right? Which means that you're not going to get exact values, right? But can you imagine square root of that guy squared plus that guy squared, then you get 7.234, right? You just get a horrible decimal. And can you imagine doing the angle and getting the tangent of theta is 1.234, and you just do an inverse tangent and you get 17.1 degrees or whatever, right? So I'm skipping by the non-exact value. And now we're going to look at conversions of formulas. Right? In particular, how to convert Cartesian to polar equations. So we're going to take formula. Did somebody say 6x equals 7y or something? Because maybe I could do that one first.
Yeah, it was 6x equals 6y.
Right. So what you basically have here is an equation. It ends up actually being a bit weird the way it's written. It ends up being the straight line y equals x, right? But for whatever reason, they jumbled it up. Are you happy about, we'll just leave it alone, right? So how do you do the conversion? You use the fact that x and y can be turned into r cos theta and y can be turned into r sin theta. And not for this question, but for some questions. You can also use the fact that x squared plus y squared is equal to r squared. So let's put it into practice in this one. 6 times r cos theta equals 6 times r sin theta. So I've just replaced the x with the x and the y with the y. Wasn't that painful, right? Do you think I'm going to leave it like that, or do you think I'm going to try and make it look pretty? Yeah, going to try and make it look pretty. Simplify is the proper term, but I think of pretty and ugly, right? So what are we going to do here to make this simpler?
Is our goal here to get like r or theta by itself? Or
If you can, or if nothing else, get it at least. You typically try and get r by itself, but that isn't going to happen in this question, but typically you do. And if you can't get r on its own, at least make it simpler, right? Reduce it to the point where you can write it in its simplest format. So r equals or theta equals would be your goal. In this case, it's eventually going to be a theta equals. So what could I do to both sides to simplify this equation?
divide by 6?
Okay. Can I do more?
Divide by r?
We're on the right tracks. As long as you do it to both sides, it's okay, Ro. So both those lines are valid. We're assuming r isn't 0. If r was 0, it would be the origin. That'd be a special case anyway. What can I divide both sides by now to get that to be simpler?
Cosine?
You remember we did some kind of equation that had that kind of situation, and you ended up with a tan, right? In this case, don't you end up with tan that looks like that? Agreed? Now, that is pretty simple, but the goal is to make it r equals or theta equals, right, depending on the question. I can do even better than that. What angle has a tangent of equal to 1?
Pi over 4 or 5 pi over 4.
Yeah. Now, if you use this version and then you allow r to be negative, you've got everybody. So that is your final answer. In polar form, 6x equals 6y equals pi upon 4. Theta equals pi upon 4. Now, if you imagine, what would that be? That's all the points that make an angle of pi upon 4. Right, can you imagine this angle here is pi upon 4? If you choose all the points on it, do you see you get that straight line? Now, what happens if you make r go negative? Do you see you get all the other half of that straight line? So do you see pi upon 4 essentially covers all the points on that equation up there. Now I'm going to give you a really easy one and then a really horrible one to finish. This one is a really easy one. X squared plus y squared equals 16. You know that's a circle if you draw it, right? You want to replace it into polar form. Is there anything I can replace x squared plus y squared with?
4? Oh.
Oh, well, eventually that's r, you're right. But there's a kind of line before that for the others who don't get that. X squared plus y squared can be replaced by?
Square rooted?
By?
Oh, okay.
Okay, maybe it's so obvious it wasn't obvious, right? You were thinking too hard, right? You agree that x squared plus y squared is the same thing as r squared, right? That's the relationship between the two. Now, we want r on its own, and you pick positive 4. Remember, r should be positive, and theta should be between 0 and 360, or 0 and 2 pi, right? So that's why I chose that number and not any other choice, and that's why I'm picking r equals 4. The scary one, darn it if I can remember what it is, so if you hold on a second, I'll find a version of it.
Is it question 20 on 8.1?
I'm pretty sure it's the last one or the second last one. It's question 20, yeah. So let me zoom back. Here we go. How do you convert from polar back into X's and Y's, right? The other direction. For the most part, these guys turning into polar are relatively straightforward, right? All the X's get replaced by R cos theta, all the Y's get replaced by R sin theta. And then you try and make it as pretty as you possibly can, which means you try and make it R equals a function of theta, or theta equals some number, right? That's your goal. Now, this fella, not so obvious. First thing I'm going to do is cross multiply. So that's going to be R 1 plus 2 sine theta equals 4. So my goal eventually is to have everything with X's and Y's in it. So if I multiply this out, I get R plus 2R sine theta equals 4. Are we okay with where I am right now? Now, there's only one piece of this puzzle right now. That I can actually do anything about. See this guy here, isn't he Y? So I have R plus 2Y equals 4. So I'm nibbling at it a little bit at a time, right? My goal is to get nothing but X's and Y's when I'm finished, right? What about R? Can I turn R into something?
X squared plus Y squared?
And because it's only R, I have to do the square root of it. Now, at this point, we're only halfway through, but at least at this point, haven't we get rid of the R and the thetas, and we've now got nothing but X's and Y's all over the place? And you might say, great, I'm finished. I want to leave this question right now. But no, we have to simplify it if it's at all possible, and it is. And so you might say, well, what does simplification look in this case? It looks like I don't want any square roots. That's what it looks like. So I am going to subtract 2y from both sides. Okay, now as long as you do it to both sides, it's okay rule. Been using that a lot. What could I do to both sides to get rid of that square root that I just don't want to be there?
Square everything.
Which gives me x squared plus y squared equals that guy, right? Square everything. This guy eventually gets you this guy. Can you trust me on the 4 minus 2y times itself gives me this, right? You can check it later. Right, I'm about 90% finished here. Right, I've got rid of the square roots. I've got all the things in x's and y's. That's 90% done. We just have a little tweak here. When you get an equation that's got x's and y's all jumbled up like this, it's called an implicit equation. And the rules for implicit equations are you try and make it so everything that is a variable goes on the left, right? Essentially. So what I'm going to do is I'm going to subtract 4y squared from both sides. I'm going to add 16y to both sides. And I'm going to subtract 16 from both sides. And now we are finished. So this equation 4 over 1 plus 2 sine theta is the worst question that you're going to get in your homework, or a version of this. And I am